Good morning, children. Today's class, we are starting a new lesson, chapter 10, circles. What is the definition of a circle? A circle is a closed figure whose each point is at a constant distance from a fixed point. That is, a closed figure in which each point is at a constant distance from a fixed point. The fixed point O we call as the center of the circle, and the constant distance of O and any point, we call it as the radius of the circle. And in this lesson, we will be discussing about certain properties possessed if a line and a circle are given to you. Imagine a line and a circle in a plane. What are the three possibilities? The three possibilities are: the first case, the line and the circle do not touch or intersect each other. The second case, the line intersects the circle at 2 points A and B. Whereas the third case, the line touches the circle exactly at 1 point. So the first case, the line and the circle do not intersect or meet or touch each other. The second case, the line is intersecting the circle at 2 points, and the third case, the line is touching the circle at exactly 1 point. We can define these lines by special name. A line which intersects a circle at 2 points is called a secant line. A line which touches the circle exactly at 1 point is called a tangent line. So these are the definitions of a secant line and a tangent line. This lesson deals with more properties about a tangent line. As we have defined, a tangent line is a line which touches the circle exactly at 1 point. In the figure, we call XAY is a tangent. That is the way of reading by including the point of contact. So, in the figure, XY is a tangent at the point of contact A. At the point of contact A. Since A lies on the circle and the line is exactly touching the circle at the point A, the question is, how many tangents are there for a given circle? Since a circle is made up of many points, at each point you can draw a tangent which shows that there are infinite number of tangents. There are infinite number of tangents for a given circle. So the first condition is there are infinite number of tangents for a given circle because A circle is made up of infinite number of points, and at each point there can be a tangent. The second property, imagine you are given a circle with center O. Consider a secant for this circle as PQ, or the 2 points on the circle we are taking it as PQ. Imagine you are drawing secants to this given secant in a parallel way. When you draw the secants, you can see the length of the chord getting reduced as you move away from the center, and when you reach a point here, you can see that secant turning as a tangent at the point A. Similarly, on this side also, you will get a tangent at the point B. Or how many parallel tangents are there for a given circle? That is the question. The question is, if you are given a circle and one of the tangents as P, A, Q, how many more parallel tangents can be there is only one more tangent which can be parallel to the given tangent, or a circle can have only 2 parallel tangents. A circle will have only 2 parallel tangents as shown in the figure. That is the second property of tangents. The first theorem in this lesson. The theorem states that the tangent at any point of a circle That means I am drawing a tangent at the point A. The tangent at any point of a circle is perpendicular to the radius at the point of contact. That means if we take A as the point of contact, if we join A with the center of the circle, you will get one of the radius, and the theorem says that this OA will always be perpendicular to XY, or angle OAY will be 90 degree. So if you consider the tangent in this specific, at this specific point, and the radius will be drawn in such a way, and this angle will be 90 degree. That is how the proof statement says. So once again, tangent at any point of a circle is perpendicular to the radius at the point of contact. So after drawing the figure, what is the given condition? Given condition is a circle with center O, XY is a tangent at the point of contact A. Contact A. What is to prove? To prove is OA perpendicular to XY. That is what we have to prove. And now, how the proof we are taking as, let P be any point on XY other than A. That means except the point A, take a point P on XY. So, proof, let P be any point on xy other than A. What is the property of a tangent? The tangent touches the circle only at one point, and that point is already A. So what can you say about the position of the point P? The point P is always outside the circle. Therefore, point P lies outside the circle. The point P cannot be on the circle because A is the only point on the tangent which is on the circle. What will happen if P is inside the circle? Suppose P is inside the circle, then AP will become a secant. Imagine P is inside the circle. What will happen when you join AP? It will become a secant because A is a point on the circle, another point can be there here which is touching the circle, or which shows that if you join AP, the line AP is a secant. So definitely the point P has to be outside the circle. Or if P lies inside the circle, then xy is a secant and not a tangent. That is, the point P can be only outside the circle. So what can you say about the length OP? If the point P is outside the length, what can you say about the length OP? Therefore, OP will be greater than the length of OA, and if P takes any point on this line other than A, definitely the length of OP will be greater than OA. So how do you present this point is, this is true for any point on xy other than A. That is, wherever P is taken on the tangent xy, the length of OP will be bigger than OA. That is, OA is the shortest. However, you take point P on the tangent xy, OA will be the shortest line segment which is falling onto the tangent xy. And now, if you have a point P, if you have a line xy, suppose you are drawing lines from the point P to the line xy. Did you learn a property? That perpendicular is the shortest. So, what is that property? Of all the line segments that can be drawn from an external point, the property says that the perpendicular is the shortest. Here, of all the line segments drew, we understood that OA is the shortest, or OA is a perpendicular and OA is the radius of our circle. That is, which shows that OA is perpendicular to xy, and what will be the reason you will be giving of all the line segments that can be drawn from an external point, comma, the perpendicular is the shortest. The perpendicular is the shortest. Hence, the proof is done. So, once again, given a circle, let P be any point on xy other than A. So, the A is the only point on the circle which is touching the line segment. So, if you take any point on xy, definitely that point P will lie outside the circle. Or if the point P lies inside, definitely xy cannot be a tangent. It has to be a secant, which is not given in the proof. So, immediately the length of OP will always be greater than OA, and wherever you take the point P on the tangent xy other than A, this happens, or OA is the shortest distance, which shows that the shortest distance is a perpendicular and OA represents the radius. Thus, radius is perpendicular to the tangent at the point of contact. Exercise 10.1 is based on this theorem. Exercise 10.1, question number 1. How many tangents can a circle have? The question number 1. How many tangents can a circle have? As I explained, a circle is made up of many points. At each point there can be a tangent, and so a circle will have infinite number of tangents. Circle can have infinite number of tangents. Second question, fill in the blanks. A tangent to a circle intersect it at exactly one point. It can intersect or it can touch the circle exactly at one point. A line intersecting a circle in 2 points is called a secant line. A circle can have dash parallel tangents. A circle can have a maximum of 2 parallel tangents. The common point of tangent to a circle and the circle is called the point of contact. The point where the tangent touches the circle is called the point of contact. Question number 3. Mark it as a very important 2-mark question. A tangent PQ at a point P of a circle. So read the question carefully. A tangent PQ at the point P of the circle of radius 5 meets a line through the center O at the point Q. The tangent is PQ, a line through the center O. And the radius of the circle is 5 centimeter. Meets a circle at O, and the distance OQ is equal to 12 centimeter. Find the length of PQ. And now it is given in the figure that OP is equal to 5 centimeter, OQ is equal to 12 centimeter. And now PQ is a tangent. Proof. PQ is a tangent. Why is it a tangent? Because it's a line touching the circle at exactly one point. OP is a radius. OP is the radius. What can you say about angle OPQ? Therefore, angle OPQ is equal to 90 degree, because what is the reason? In a circle, tangent is perpendicular to the radius at the point of contact. Or you can say radius is perpendicular to the tangent at the point of contact. Now, if angle OPQ is 90 degree, then therefore triangle OPQ is a right triangle and OQ is the hypotenuse. Opposite to right angle, that side are always the hypotenuse. So, by applying Pythagoras theorem, in triangle OPQ, OQ square is equal to OP square plus PQ square by Pythagoras theorem. That is 12 square is equal to 5 square plus PQ square. 144 is equal to 25 plus PQ square. PQ square is equal to 144 minus 25, 119, or therefore PQ is equal to square root of 119 centimeter. That is the length of PQ, the tangent. The length of tangent is root 119 centimeter. That is option D. The last question. Draw a circle with two lines parallel to a given line such that one is a tangent and the other one is secant to a circle. So, as a rough figure, they have told you that they have given a circle and a line outside. You have to draw a line which is a secant as well as another line which is a tangent, and both have to be parallel to the given line. The tangent will be the line M with the point of contact A, and secant will be line L, and all these three lines are parallel to the given line L. Moving on to the next important property. You are given a circle and a point inside the circle. How many tangents you can draw from this point? How many tangents? There cannot be a tangent possible in such case. Imagine the point P is on the circle. How many tangents? There can be one tangent if the point P is on the circle. What is the possibility when the point P is outside the circle? So, I have taken the three cases as the first case, given a point P inside the circle, there are no tangents possible. If the point P lies on the circle, there is exactly one tangent, and if the point P lies outside the circle, here point P lies inside the circle, P is on the circle, and in the third case, P lies outside the circle. If P lies outside the circle, we can draw two tangents as PQ and PR. So, this is the property. If a point and a circle is given to you, if the point lies inside the circle, there are no tangents possible. If the P is on the circle, there can be exactly one tangent, and if the point P lies outside the circle, two tangents are possible. And the next theorem is based on the external tangents, that is the tangents which are drawn from an external point. What is the property possessed by those tangents? Theorem 2. Length of tangent segments from an external point are equal. Length of tangent segments from an external point are equal. That means we already saw that two tangents can be drawn from an external point, and the theorem says that those two tangents will be of equal length. Let's prove. Let's draw the figure. Given a circle with center O, let P represents the external point, let PQ represent the first tangent, and PT represents the second tangent. So given a circle with center O, there, PQ and PT are two tangents from the external point P. And what is to prove? To prove the length of tangents from an external point are equal. That means what we have to prove is PQ is equal to PT. And what is the construction? The construction is join OQ, OT and OP. Join OQ, OT and OP. Now you can see two triangles OQP and OTP. If we prove those two triangles are congruent, PQ is equal to PT will be as the corresponding parts of congruent triangles. So let's prove the triangle OQP congruent to triangle OTP. So prove in triangles OQP and OTP, you can mark this angle as angle 1 and angle 2. You can see OQ as a radius, PQ as a tangent at the point of contact Q. Similarly, OT is a radius, PT is a tangent at the point of contact T, which shows that angle OQP and angle OTP both are 90 degree. By the theorem, radius is perpendicular to the tangent at the point of contact. So angle 1 is equal to angle 2 is equal to 90 degree. Radius is perpendicular to the tangent at the point of contact. That means based on the previous theorem. And now OQ is equal to OT radii and OP is equal to OP common. Therefore, triangle OQP is congruent to triangle OTP by right angle, hypotenuse, side. That means we have considered OP, we have considered angle OQP as 90 degree and the radius OQ, which shows that the congruence condition is RHS. Therefore, PQ is equal to PT as CPCT. The length of two tangents from an external point are equal and hence it is proved. This is an important 3-mark theorem.